Welcome all. So, till now we have covered the design examples covering steel beams, concrete beams. After that, we also looked into the different failure mechanisms. We looked into the buckling failure mechanisms. We looked into the tearing failure mechanisms. Okay. So, today in this week, we will be looking into the dynamic bucklings, the behavior of bucklings in the system. Okay. So, let us deep dive into the things. So, definition of dynamic stability. Okay. What is dynamic stability? Okay. So, dynamic stability. Okay. So, dynamic stability. So, the instability of the structures under time varying parameter loading is defined as the dynamic stability. Okay. So, a structure is said to be dynamically unstable, okay, if there is an instability of structure under time varying parameters, okay, time varying parameter. So, if any sort of instability occurs, okay, this is called the dynamic instability. Okay. So, distinction. Okay. So, how it is different from static stability. Okay. So, the driving term multiplies displacement coordinates, okay, not the right hand side forcing function. Okay. So, whatever is happening, it is happening in the system itself. Okay. This is not caused by due to the influence of the forcing function. Okay. So, let us look into the formulation for the bars under axial loading. Okay. So, this is the equation. Okay. So, this is the inertial part. Okay. This is the bending part. Okay. So, here what we are considering is this is a beam. Okay. So, boundary condition can be anything. Okay. And there is a loading applied here. Okay. So, due to this loading, okay, due to the axial effect, how this bar is going to buckle, okay, how the instability will creep up. Okay. EI, this term, okay, determines the bending resistance. Okay. This is the inertial term. Okay. And this term, okay, will tell us about the loading that is going to cause the instability. Okay. So, in which EI is the bending stiffness, this term is that bending stiffness, rho is the linear density. So, this is an inertial term. Okay. So, this is the resisting stiffness term, and x and t are the axial coordinates. Okay. X is the coordinate along the length and t is the time varying parameter. Okay. Load P multiplies displacement. Okay. The instability is parametric and it is not caused due to the direct forcing function. Okay. So, dynamic buckling, okay, what is happening in the core form. Okay. So, buckling in the vibrations. Okay. So, the vibration buckling, the axial load oscillates at a frequency twice the lowest bending frequency, okay, of the unloaded bar. Okay. So, the frequency of oscillation, okay, of the load is twice of the natural frequency of the system, okay, twice of the lowest bending frequency of the system. So, what is happening? Each time the bar bends to one side, okay, let us say bar is bending to one side, the axial load approaches its maximum and induces additional bending. Okay. So, if the bar is trying to bend like this, this axial force, okay, approaches its maximum value and it induces additional, the secondary bending in the system. Okay. The shape and oscillations closely resemble those caused by a lateral load, okay, that excites the mode of the vibration. Okay. So, the shape of the oscillation, okay, this shape that is caused due to this axial loading, okay, this shape is closely resembling, or it is closely resembling that is being occurred by due to an lateral loading. Okay. So, this vibration mode is being excited. Okay. So, in the absence of damping or any other non-linear effect, okay, the result is unbounded growth, okay, that is the resonating force vibration, okay, which is a topic of importance. Okay. So, with an axial load PT, okay, the motion becomes resonant of the dynamic buckling. Okay. So, the buckling caused by this axial load, okay, causes resonance in the system. Okay. And this is a case of dynamic buckling. Okay. And this buckling is also called the vibrational buckling due to its similarity to the resonant vibration. Okay. So, what is happening here is that if a system, okay, if a system is being acted by the lateral force, the system is going to oscillate in the first mode like this. in the second mode it is going to oscillate like this. Okay. When the system is acted by an axial load, okay, so this will cause the instability. Okay, this will cause the buckling in the system. Okay, and this buckling, okay, the form of this buckling, since this form of this buckling is similar to the vibrations of the system, so this is called a vibration buckling. Okay, as though the system is being acted by an lateral load. In addition to the vibration buckling, there is also a phenomena called the pulse buckling. Okay, so first we dealt with the vibration buckling. In vibration buckling, what was happening is that the lateral load was causing the buckling, and the shape was similar to that caused by a motion due to the lateral loading. Okay, so this was called the vibration buckling. Okay, so similarly pulse buckling occurs. Okay, so in pulse buckling what happens is that the load is applied as a single pulse of amplitude much greater than the static buckling load. Okay, this occurs, for example, if the bar impacts a massive rigid object at velocity v. Okay, so the bar is hit by a massive rigid object at a velocity v. Okay, the resulting impact stress, okay, rho cv, okay, where c is the axial stress wave velocity, can exceed the static buckling stress for higher order modes, okay, with short wavelengths, even at the modest velocities. Okay, so here what is happening is that the system sees a single pulse. Okay, the system is acted by a single pulse. Okay, the system sees a loading, okay, which resembles a pulse loading. Okay, so pulse loading, we have seen that our approximation was that if T over Tn, okay, is less than 1/4, okay, so then we can consider the applied loading as a pulse loading. Okay, so here we are dealing with the pulse loading. Okay, so if a pulse loading is applied, okay, which has an amplitude which is much greater than the static buckling load, okay, the amplitude of this thing is greater than the static buckling load, okay, PCR. Okay, this can occur, okay, if the bar is impacted by a massive object at an velocity v. Okay, so the resulting impact stress, okay, the impact stress is given by the equation rho cv. Okay, c is the axial stress velocity. Okay, can exceed the static buckling stress for higher order modes with short wavelength. Okay, so the stress caused by this impact exceeds the static buckling stress, okay, for higher modes with short wavelength, even at the modest velocity. Okay, even if the velocity v is small, relatively small, the impact stress caused by this phenomena, okay, exceeds the value of the static buckling. Okay, so this leads, okay, what happens here is that this causes a buckled shape, okay, consisting of multiple waves along the bar length. Okay, so if this is the bar, if this thing has been hit by a velocity v having a rigid mass, okay, so here the buckling might occur. Okay, so there might be multiple waves along the length of the bar. Okay, this happens, why this happens? This happens because the resulting impact stress, okay, it's significantly more than the static buckling stress. Okay, so this causes a wave-like motion. Okay, it causes a buckled shape, okay, consisting of a wave-line, multiple wave-line shape. Okay, so while the load is applied, the buckling increases monotonically instead of oscillating as in vibration buckling. Okay, so in vibration buckling, okay, this is being caused. Okay, but in pulse buckling, this type of wavelength will be caused. Okay, the sketch, okay, idealizes the buckled shape to a single mode. Okay, so we will see the buckled shape for a single mode. Okay, so in reality, actual cases may involve axial wave propagation and other complexities. Okay, because buckling is induced by a single strong load pulse, this dynamic buckling is termed as pulse buckling. Okay, since this buckling is caused by a single pulse type of loading, okay, it is being caused as a pulse buckling. Okay, in the previous case, okay, the buckling was caused due to an axial loading where the shape was consistent with the vibration of the system. So this was called the vibration buckling. Okay, but here, since the buckling is caused by a single strong pulse, okay, this is called a pulse buckling. Okay, where the buckling shape propagates along the length of the system. Okay, so this is the case for a vibration buckling, and this is the case for a pulse buckling. Okay. So in vibration buckling, again the shape of the vibration buckling, okay, resembles that of a equivalent to the deflected shape caused by a lateral load. Okay. So actually the buckling is caused by the effect of this loading, okay, and the buckling is in this shape, okay, but it looks like that the system is under the influence of a lateral load. Okay. So this is called the vibration buckling. Okay. Okay. And in pulse buckling, okay, the system is acted by an effect of the single pulse. Okay. The loading is represented by a single pulse. This can be due to a high velocity loading, okay, consisting of a rigid mass. Okay. And the buckling mode, okay, travels along the length of the beam. Okay. So this is the pulse buckling. Okay. Pulse loading we can approximate if T over Td is less than 1 over 1/4. Okay. So if the time period is short as compared to the natural period of the system, then we can approximate the loading as a pulse loading. Okay. So this is an example of a vibration loading, and this is an example of a pulse loading. Okay. So now we are looking into the dynamic buckling in the form of a core. Okay. So here the figure presents this is a high speed picture. Okay. This is a high speed picture of an aluminum strip after the impact against a massive jaw at the bottom of the images. Okay. So this is a picture from a high speed camera, okay, of an aluminum strip. Okay. So this shows the buckling in the core form. Okay. So here we are seeing the total length of the strip. Okay. Here we are seeing the thickness of the strip. Okay. And the boundary condition is the clamped boundary condition, meaning the fixed boundary condition. Okay. So as the time progresses, we see the buckling that is occurring in the aluminum strip. Okay. So here what we can see is that with the progress of the time, we can see the evolution of the buckling that is occurring in this strip. Okay. The impact condition was created by pulling the strip, okay, much longer than the portion shown. Okay. So here a short portion is shown, but in reality the length, okay, that is being pulled is very much longer than the portion that is being shown. Okay. So using a tensile mechanism, the entire strip is being pulled. Okay. So this is a long strip. Okay. So this is being pulled. Okay. And then suddenly cutting it near its upper end with small explosive charge. Okay. So if we draw the schematic of the experiment, okay, it will look something like this. Okay. There is a long strip. Okay. Okay. And it is held here by a jaw mechanism. Okay. And in the top, okay, so this is a fixed mechanism. Okay. It is held static at this position. Okay. Here this is being pulled. Okay. So this is being pulled, and suddenly after being pulled to a certain extent, this pulling mechanism here, one explosion occurs, so that this pull thing is suddenly released. Okay. So using a small explosive charge or any other mechanism, this pull is being released. Okay. And here, okay, we are taking the photograph of an intermediate position. Okay. We are taking the photograph of this intermediate position. Okay. So here we can see the clamped boundary condition and the rest of the strip. Okay. So once this is being pulled, okay, what happens? Okay. The sudden cut, okay, due to any explosion or any other mechanism, produces a compressive relief wave. Okay. The system is relieved from the extent of the pull. Okay. And it tries to bounce back. Okay. So there is a compressive wave, okay, that is trying to travel down across the cross section of the strip. Okay. So it's traveled downward to the jaw, and again it is reflected back as a compressive wave. Okay, generating an axial compression equal to the initial tension in the strip. Okay. So once this strip is released, okay, this tries to come down, okay, to its natural position. So a compressive wave travels like this, and after hitting the boundary, again it tries to travel back. Okay. So once this happens, we can see the propagation of the waves here, okay, and due to this compressive action, okay, the buckling, you can see the formation of the buckling in the strip, okay. So this axial compressive wave, okay, is causing the buckling in the strip, okay. So this is an example of the visualization of the buckling, okay, which occurs in the strip, okay. Okay. So features of the buckling. So buckling is more concentrated near the impacted end, okay. So we can see the buckling is concentrated near the impacted end, okay. The axial load persists the longest at the impacted location, okay. Any eccentricity introduced at the jaw is locally amplified by the buckling. If any eccentricity is present, okay, that is being amplified due to the buckling phenomena, okay. So if we further analyze the bar, okay, using an eccentric type of impact, okay, if the mechanism, the pulling mechanism is not at the center, but it is located at an eccentricity, okay. So then we can also use it for the visualization of the buckling behavior, okay. So this will be in addition to the already occurring buckling in the system, okay. So this major feature of the observed buckling form closely resembles those observed in the previous figure, okay, where the idealized sketches illustrate the vibration and the pulse buckling, okay. So this is resembling the buckling behavior, okay, that we have already seen in the previous figure, okay. Here we can see that it is mimicking this type of buckling behavior, okay. This type of buckling behavior is being mimicked, okay. So here this is a theoretical approximation, and here we can see we have the actual visualization of an experiment where the high speed photograph has been taken and the evolution of buckling is being shown out here, okay. Okay. So a key phenomena seen in this experiment is that the pulse buckling tends to form a characteristic wavelength, okay. Here if you see, okay, okay, a wavelength type of motion is being formed, okay. So that was the signature. If you looked into this figure, we can see the propagation of the wavelength, okay. So it tends to form a characteristic wavelength, okay. This is occurring because a band of preferred mode grows more rapidly than other, okay. So here what we are doing is that we are forcing it to buckle in a particularly preferred mode, okay. So that's why we will see the formation of that wavelength which corresponds to that particular mode, okay. The wavelength of this preferred mode depends upon the pulse amplitude rather than the bar length, okay. So the cause, okay, the reason that is causing this buckling, okay. So here it was a case of sudden release of the bar, or it may be, in other cases it may be due to the extent of an impact, okay, which occurs with a high velocity, okay. So the formation of this particular mode, okay, let us say we have a theoretical mode like this, okay. So the formation of this theoretical mode, okay, the formation of this theoretical mode will depend upon the amplitude of the pulse, okay, rather than the bar length, okay. So the higher the mode, okay, higher the extent of the pulse, okay, okay, higher the magnitude of the pulse by which this bar is being hit, okay, this will cause it to form in this particular higher mode, okay. So this mode will depend upon the magnitude of this loading, okay, it will depend upon the pulse amplitude, okay. So there is a distinction between the clear distinction between the pulse buckling from the vibration buckling, okay. So in pulse buckling mode, okay, the pulse buckling mode depends upon the loading, okay. So here we have seen the formation of this particular mode will depend upon the magnitude of this pulse, okay. So the formation of pulse buckling mode will depend upon the loading condition, okay, and it must be resolved through the dynamic analysis, okay. So if you do the dynamic analysis, we can see what type of mode it is going to happen, okay. But in the static buckling, okay, the lowest modes are naturally excited and can generally be determined independent of the buckling mode. Okay. So, in vibration modes, okay, normally first the lowest mode will be excited, okay, and so in the starting we will see the formation of the buckling, okay, in the lowest mode. Okay. So, in the vibration mode, first it will start to buckle in this mode, after that it will buckle in the second mode, and it will, after that it will buckle in the third mode, and so on and so forth. Okay. But in pulse buckling, okay, the buckling mode will depend upon the amplitude of the pulse that is it is being hit with. Okay. But in the vibration mode, it traditionally the lowest mode will be excited first, and it will grow with the increasing mode. Okay. So, this is one of the key differences between the pulse buckling and the vibration buckling. Okay. Pulse buckling depends upon the magnitude of the pulse. In the vibration buckling, it will not depend upon the magnitude of the externally applied loading, but it will start from the lowest mode and it will grow further. Okay. So, here, okay, again we are seeing a high speed camera photographs of the buckling modes taken. Okay. So, this figure shows a sequence of a framing camera photograph of a thin walled cylindrical shell. Okay. So, in the earlier case we were having the aluminum strip. Okay. In this case we are having a thin walled cylindrical shell. Okay. So, earlier case a strip was there, now a thin walled shell is there. Okay. In the previous case, okay, the bar was stretched, okay, and it was released suddenly, okay, due to explosion or any other cutting mechanism. But in this particular case, a thin walled cylinder is being taken, okay, and it is impacted at the lower end. Okay. And the magnitude of the impact, it has an axial stress of 1.5 times the classical static axial buckling stress. Okay. So, the amount of hit, okay, the magnitude is 1.5 times the classical axial buckling stress. Okay. So, also the shell has a higher radius to thickness ratio. Okay. So, the radius to thickness ratio is also large. Okay. So, here if we can closely see, okay, you can see the formation of the buckling pattern at this ends. Okay. So, the impact is generated by clamping the shell to a massive internal ring at its base and suddenly projecting the ring upwards via an explosive into stress waves in a massive anvil. Okay. So, how it is being generated? Okay. So, what is happening here is that the shell is clamped to a massive internal ring at its base. Okay. So, here clamping mechanism is there. Okay. It is being clamped out here, and then this thing is being propelled. Okay. So, there is an rigid mass here, okay, and it is being propelled upwards, okay, via the use of any spring mechanism or in this particular case an explosive mechanism. Okay. So, ripples start from near the clamping ring similarly to the bar. Okay. So, in the earlier case also, okay, since the compressives were coming at the end, hitting here and going back, so the buckling was starting at the ends only. Okay. So, here also ripples are starting near the clamping ring. Okay. So, here if you can see, okay, we can see the formation of the ripples. Okay. We can see this type of formation, okay, which are occurring near the clamping ring, okay, similar to the previous example. Okay. But in this shell the ripples are two dimensional, okay, with clear wavelengths in both circumferential and in axial directions. Okay. So, here we can see the waves are going in the radial direction also, okay, they are moving in the radial direction also, and they are moving in the axial direction also. Okay. So, the movement of the waves are two dimensional, it is occurring in the axial direction also and the radial direction also. So, radial as well as axial direction, in both these things we can see the formation of the buckling shape. Okay. So, here we are showing the comparison of a dynamic and a static post buckle pattern. Okay. So, at very late times the buckle evolved into the familiar post buckle diamond shape typical of a static buckling. Okay. So, here we are showing the buckling, okay, a shape in a static buckling. Okay. And this is a case where the dynamic buckling is being shown. Okay. So, here we can see the buckling has occurred in the axial as well as in the radial direction both. Okay. So, if we looked into a post picture, okay, where the buckling has already formed, okay, So the dynamic buckling also resembles somehow the static buckling shape. Okay. The wavelength of the dynamic buckling are much shorter than those of the post buckle static shape as shown here. Okay. So we can see the pattern of this waves. Okay. So here it is much longer. Okay. The wavelength is much longer in the case of static thing, but in the case of dynamic loading, okay, in case of dynamic buckling, the wavelength is much shorter. Okay. So both axial and circumferential wavelengths of the dynamic buckles, okay, in high speed and post buckle photos agree with the classical linear buckling theory calculation. Okay. So the buckling is occurring in both the radial as well as in the axial directions. Okay. And it agrees with the classical buckling shape that we get from the static calculations. Okay. So here the buckling shape, okay, in the radial and axial direction is being shown. Okay. This is being caused for a dynamic loading, and this is our simple static loading. So in the simple static loading, what is being done here is that there is a cylinder, it is being held between a fixed plate, and this axis tries to move downwards. Okay. And what it does is that it tries to buckle this shape. Okay. So this type of wavelength formation occurs. Okay. So in the case of dynamic buckling, this was held, okay, and there was a rigid anvil and it was propelled up. Okay. So it hit here, the wave traveled at the downward position. Okay. The compressive wave traveled at the downward position, reflected back, and there was the formation of the buckling. Okay. Similar to what was occurring for the aluminum strip case. Okay. And here if you can see the closely spaced photographs here, the dynamic buckling is occurring here. Okay. Okay. The static post buckled pattern exhibits longer wavelength than dynamic buckling due to the complex nonlinear motion occurring after initial instability. Okay. So here the wavelength is longer than the dynamic buckling. Okay. So the longer wavelength static buckling is characteristic of the imperfection sensitive structures. Okay. So this is normally caused due to the imperfection that is inherent in this type of structures. Okay. With the cylindrical shell as the prime example. Okay. So the cylindrical shell exhibit this type of longer wavelength. Okay. And this is the typical formation of the buckled shape. Okay. In the case of a static buckling. Okay. A third type of dynamic buckling is the lowering of static buckling loads caused by the suddenness of an applied long duration load. Okay. So there is also a third type of dynamic buckling, okay, in which the static buckling loads, okay, the buckling is caused by loads lower than the static buckling loads. Okay. And this is due to the application of a suddenly applied long duration load. Okay. So here we are talking about the pulse that is applied for a very short duration. Okay. Then we talked about the vibration buckling. Okay. A third type of buckling is there when there is a longer duration loading is of longer duration. Okay. And the buckling is caused due to this longer duration load. Okay. So in the case of a application of a longer duration load, okay, both static and suddenly applied loads are significantly lower than the classical linear elastic buckling loads. Okay. So here buckling is occurring due to a load, okay, which has a lower value than the classical linear elastic buckling loads. Okay. And the non-linear buckling is triggered at the lower loads, okay, than the static reductions caused by the non-linearity. Okay. So here what is happening is that the pulse duration is large, okay, the loading duration is large, and the buckling load that is being caused, okay, P buckling, okay, that is causing the buckling phenomena, it is significantly lower than that what is the load required to cause the buckling in a static sense. Okay. So the value of P is significantly lower than the value of P static, okay, and it is a long duration load. Okay. So we have three types of buckling mechanism. One, it was caused by the pulse buckling, one was caused by the vibration buckling, and the other one is caused by an long duration loading, okay, where the actual magnitude of the buckling load is lower than that of the static load. Okay. A fourth type of dynamic buckling arises in designing shape charge and explosive pipe closures. Okay. So there is a fourth type of buckling. Okay. which is seen, okay, in when we are talking about the design of the shape charges, okay, and explosive pipe closures. Okay. So, sometimes we have to keep the explosives in the pipes, okay. A pipe type of enclosure is there. Okay. So, what happens there is that rapid accurately timed closure of pipe via detonation explosive charges around them tends to produce high mode buckles that can disrupt the uniform wall collapse. Okay. So, here, okay, what will happen is that the buckling mode will cause there will be a higher buckling mode, okay, and that will prevent the collapse of the uniform charge. Okay. So, in this type of closed enclosures also a buckling mode occurs. Okay. This pulse buckling effect differs from others in that the load must be intense enough to prevent buckling rather than keeping it low. Okay. So, here the load is significantly higher, okay, to prevent the buckling phenomena. Okay. So, many other types of dynamic buckling exist in the literature, okay, but are not extensively treated here. Okay. So, here we are showing the pulse buckling, okay, we are showing the vibration type of buckling, we are showing the buckling where the load duration is large, okay, and the magnitude is less, and again we are showing buckling in which the collapse of the wall is being prevented. Okay. And other type of buckling also exist in the literature, okay, which are not shown out here. Okay. So, the examples of other type of bucklings are flutter enhanced bending and buckling, where bending of aerospace vehicle skins is amplified by the aerodynamic flow interaction. Okay. So, this is a complex type of buckling where the outer hull, okay, or the outer skin of any aerospace structure, okay, buckles, okay, and this buckling is a combination of the bending action and the initial buckling action. Okay. So, here there is a merger of the two type of buckling, okay, merger of the vibration and the pulse type of buckling, where the buckling in any other type of structures occur as a combination. Okay. One more example is snap through of arches and domes, okay, involving asymmetric deformation mode that reduces strain energy compared to the systematic snaps. Okay. So, this type of buckling occurs in the arches and the dome type of structure, okay, where there is an asymmetric deformation, okay, and due to this there is a reduction in the strain energy and the buckling might occur in this type of structures. Okay. So, due to the various instabilities, okay, various dynamics instabilities are encountered in engineering, okay, and they include those arriving due to the interaction between the control system and the structural responses. Okay. So, whenever there is a mismatch in the stability, okay, a new type of buckling can occur. Okay. So, after this thing we will be focusing buckling on simple bar, rings, low cylindrical shells and finite length shells with simple supports, okay, where dynamic buckling theory is most straightforward. Okay. So, now we have looked into the different buckling phenomena. We have encountered the different buckling phenomena such as pulse buckling, vibration buckling, okay, buckling due to longer load, buckling where the uniform load is suppressed, okay, combined buckling, okay, where it is a combination of the pulse and the vibration buckling, buckling in the arches. Okay. So, after that we will be dealing with the buckling in simple mechanisms, okay, where the buckling phenomena can be addressed properly. Okay. So, we will be looking into the bar, which is the simplest structural element, okay, and it can be modeled as a classic column design, okay, and all the buckling theory will be applied and then assessed, okay, to see what are the different buckling loads coming out from the different phenomena. Okay. So, we will stop here. Today we have discussed about the different type of buckling phenomena that can occur in a system, its complex interactions, given some examples, and in the next class onwards we will be discussing about the classical mechanisms applied to the buckling phenomena occurring in simple structures such as bars, beams and the other systems. Thank you.